In this video, we will show the demo of two methods to create matrix multiplication in C. In this test, we are going to use the square matrix to avoid confusing array management. We are going to explain how each function works first. After that, we will be showing the result in real time to give examples on how optimization in the right way can greatly reduce working time. And lastly, explain how block matrices actually work. Let's start on how each function works with the flush all caches function. The flush all caches function is designed to remove any data from CPU cache that could impact the performance measurements of code that runs after this function. This is especially relevant in benchmarking or when you want to measure the time taken by a specific operation without the advantage of cache speeds. After finding out the cache side of our machine, we use the for loop to iterate the allocated block, writing a value to each byte. And after that, we use the free function to release the memory. This part is necessary to prevent memory leaks. So the purpose of this function is to ensure that when you later measure the performance of your code, you're measuring the true performance without any artificial benefits from data being already loaded in the cache from previous operations. After that, the program will jump to the load metric base function, which is responsible for initializing and loading matrices A, B, and C into memory from input files. We input the reading. The function reads the matrix data from two input files into the allocated memory for matrix A and matrix B. The reading loops run for the total number of elements in the matrices. After that, it also initializes the matrix C to 0. So the purpose of this function is to set up the initial state for a matrix multiplication algorithm, ensuring all required data is in memory and ready for processing. Now we have a function called multiply base to perform a matrix multiplication algorithm. First, it starts by determining the size of the matrix using the line counter function, which counts the number of lines in input 1.in. This assumes the matrices are square and the number of lines corresponds to both the number of rows and columns. And then all elements of Hill matrix C are set to 0 to prepare for the accumulation process during multiplication. 3 nested loops iterate over the indices of the matrices to perform multiplication. Each element of the result matrix, huge matrix C, is the sum of products from the corresponding row of huge matrix A and huge matrix B. The index for each element is calculated considering the matrices are stored in a 1D array in row major order. The product of element A, matrix A and matrix B is accumulated into matrix C. The purpose of this function is to conduct a straightforward matrix multiplication without any optimization strategies like caching or parallel processing. Next up, we have the compare result function. This one is to compare the result of matrix multiplication operation against a reference solution. So this function ensures the integrity of the multiplication operation by verifying that the computed result matches the expected outcome. Next is the void write results function. The write results function is to write the contents of the computed matrix to the output file. So it works by calculating the number of lines, which corresponds to the size of the matrix by calling line counter from the input 1.in files. And then it uses for loops to iterate over the rows I and columns j of the matrix. Inside the inner loop, it calculates the index for accessing elements in the first-dimensional array that represents the matrix in memory. For each element, it writes the value followed by a space to the output file, fout actually. After all elements in a row are written, it adds a new line character. In essence, this function translates the 1D representation of a 2D matrix back into a 2D format in a file, making it more readable and preserving the matrix structure. Next, we have the load matrix function. The load matrix function is actually similar to load metric base. Both functions are designed to load matrix data from input files into memory, but the differences are some of the purpose. For the load metric base function might be used as a reference implementation with a basic or straightforward approach, while load matrix function might include optimizations or additional functionality. Load matrix function might have optimizations that load matrix base function does not, such as memory access patterns that are more cache friendly or parallel loading of data. Next, we have the multiply function. The multiply function in the code is designed for optimized matrix multiplication. So first, the function calculates an appropriate block size based on cache size and data type. For example, a 4 kilobit cache and long integers. The block size is computed using a formula. In this case, it results in a block size of 13. The matrices are divided into smaller blocks. The function iterates over these blocks, ensuring that a smaller contiguous section of the matrix is loaded into the cache, which can reduce cache misses. Inside the loop of the multiplication, the innermost loop is unrolled by a factor of 2. And then, in the result of the multiplication for each block is accumulated in the temporary variable sum, and then added to the corresponding position in the result matrix, huge matrix C. This function is an example of combining cache optimization to enhance the performance of matrix multiplication operations. To calculate block size, we can use the formula of square root cache size over the size of data type times number of the matrices. So what is the function workflow is to determine matrix size and then iterate over blocks. After that, it will enter the loop unrolling. So optimizing cache usage, it reduces cache misses and improves performance, while loop unrolling reduces the overhead of loop control and increases data throughput. So that was all the functions we implemented. Now let's see the runtime for both methods. In conclusion, as you can see, the block method provides a better runtime while giving the same result. This is due to the optimization we did by using techniques like block matrix multiplication and loop unrolling as explained in the multiply function. We have tested and collected the runtime 10 times to get an accurate representation of the output. The total time it took the program to multiply using the block method is usually 100 times faster than the baseline method. Also, the loading function of the block method is 100,000 times faster than the baseline method. Thank you.